Okay, section 4.4 is about indefinite integrals and net change, and it's really two main points, two different things sort of stuck together in one section because neither one of them takes very long. The first thing is just developing a notation for antiderivatives and then remembering how to find antiderivatives because we haven't done that in a while. And the second main idea is an application, that is another way of thinking about definite integrals. So if f is a function that represents a rate of change, what does its definite integral tell you? Okay, so we'll first look at antiderivatives. We've been using capital letters for antiderivatives, but that's got a few problems. So here's one big problem with it. If you have a function f of x and you take its antiderivative, we've been writing it capital F of x. But what if you want to take the antiderivative again? There's not a more capital F, so how do we write the antiderivative of that antiderivative? We don't know. So we need a different notation. The fundamental theorem of calculus told us that antiderivatives are actually related to integrals, definite integrals. So we're going to use an integral notation for antiderivatives as well. So the general antiderivative of a function will be written like this. And we say the indefinite integral of the function. So the integral without specifying a beginning and ending x value is called the indefinite integral, and it means the same thing as the general antiderivative. Remember, the general antiderivative is any antiderivative plus c, plus constants. Okay, so we have two integrals and they are different kinds of things. A definite integral goes from a to b, is a number. When you do a definite integral, you get a number. When you do an indefinite integral, you get a function, or actually a family of functions, because you get a function plus any constant. So different constants would give you slightly different functions. But the indefinite integral is a function or family of functions. The definite integral is a number. If you look in section 4.4 of the book, there's this nice table of all the rules we know so far about antiderivatives. Now we call them indefinite integrals. So the top two are telling you that you can pull a constant out of the indefinite integral and you can split up an indefinite integral with addition. We already knew that for antiderivatives, but now it's written as rules for indefinite integrals. And then the others are the kinds of functions we know how to find the antiderivatives of. The antiderivative of a number k is k times x. The antiderivative of sine of x is negative cosine of x, and so on. We will develop more rules as we go on, more strategies for finding indefinite integrals or antiderivatives, but these are the ones we know so far. And so we can find antiderivatives, right? So this is the indefinite integral of cosine theta over sine squared theta, d theta. Remember, indefinite integral means antiderivative. Well, I don't have a rule for finding the antiderivative or indefinite integral of something like this, but I can rewrite it. Cosine over sine squared can be rewritten as 1 over sine times cosine over sine. And I have other names for those things. 1 over sine is cosecant, cosine over sine is cotangent. So what I want to integrate is cosecant theta, cotangent theta, d theta. Well, now the bottom right fact in that box is exactly this, and so my answer is negative cosecant of theta plus any constant. And as always, you can check and see if you got the antiderivative right by taking the derivative of your answer and making sure it matches what you started with. So I could take the derivative of negative cosecant theta plus c, and I should get cosine theta over sine squared theta, although I'd have to rewrite it using identities to get that. Okay, on to the second point. The fundamental theorem of calculus that we learned about in the last section gives us a way to compute definite integrals without Riemann sums. Right? The definite integral of a function from a to b is antiderivative, which we can now write with an indefinite integral, and you plug in b and you plug in a and you subtract. Right? So it's the antiderivative at b minus the antiderivative at a. We've already talked about how this means, that the definite integral means the net area between the graph of the function and the horizontal axis between a and b. Right? So you draw a graph and you have the area above the axis minus the area below the axis, and that's the value of the definite integral. But that's not all definite integrals can tell you. If you look at little f and big F, right? Big F is an antiderivative of little f, so big F prime equals little f. So we can think of this definite integral as the definite integral of capital F prime, which is the rate of change of capital F. So what we're integrating is really the rate of change of capital F, and what we get as a result is the net change, the total change in capital F from x equals a to x equals b. That is, how far apart are capital F of a and capital F of b. Okay. Thus, the definite integral of a rate of change tells you the net change in that quantity. This is incredibly useful. Here's one example. If v of t is a velocity function, so it's telling me the velocity of an object at t seconds, what does the definite integral of v of t from 3 to 7 represent? Well, realize that a velocity is a rate of change. It's a rate of change of the position function. So what we're doing is integrating a rate of change. The definite integral of a rate of change is the net change, so this definite integral should equal the net change of position. I integrate the rate of change of position and I get the net change of position between these two t values. Well, that just means the position at 7 minus the position at 3 seconds. And that's known in physics as the displacement of the object between 3 and 7 seconds. So the definite integral of velocity tells you displacement. The same idea can be used in lots of other situations. We'll see them in class. The idea is the definite integral of a rate of change will always tell you the net total change in that quantity. Notice that means we have two ways to think about definite integrals. They're net areas or net change. So if you want to find a net change, you can do it by looking at a graph. You graph the rate of change and you look at the net area, area above the axis minus area below the horizontal axis, because both of those are the definite integrals, so they'll equal each other. Okay, here's a video question. I just want you to write a sentence or two telling me the difference between these two things, the definite integral of f of t and the integral of f of t for some function f. I'll see you in class.